A recap of our lab for Atwood machine. So we started with the warm-up. If we have two blocks on a string connected over a pulley, and each block has equal mass, both of them in this case are 15 kilograms. To draw the free body diagram, it's the same for both. We have the object. Because it has mass, it will have force of gravity. And that force of gravity will be equal, not to normal force, as when the object is on the surface, but it will be equal to force of tension. So Ft, or just T, whichever makes sense to you. And the second one will have exactly the same free body diagram because they have the same mass and therefore they have the same diagram. Now, comment on tension. It is equal on each one, as in T1 and T2 are identical. So I could say this is M1G, this is M2G. Will the system move? No, it will stay at equilibrium. Calculate T. Well, we already said T equals mg. So it's going to be 15 times 9.8, which is 147, and as any other force, it's measured in newtons. When we move on to case number 2, what changes is now one of the object is 10 times more massive than the other. I'm going to duplicate this real quick. The important thing to realize is that force of tension is going to be equal even now. What I mean by that is the upward force, that is force of tension, is the same. However, as far as that force of tension relates to force of gravity, that will change. For the heavier mass, we will have a greater force of gravity than tension. For the lighter mass, it's going to be the other way around. How do we know that? And if I'm saying that this is 120 kilograms versus 12 here, what is going to happen is this whole contraption is going to start rotating counterclockwise. And 120 is going to start accelerating downward. So when it says add acceleration direction, this will be the acceleration for that one, and this will have the direction of upward, the acceleration for a lighter object. Tension is still equal, definitely move, and it will definitely accelerate. Each one of them will accelerate because forces are not equal. And I'm not talking about the tension. The tension is equal between the two of them because it's the same rope. However, you are always comparing the combination of the forces on that one object. For this object, gravity is greater than tension, therefore it accelerates downward. And for the lighter object, force of tension is greater than mg, so it's going to accelerate upward. Magnitudes are the same. Opposite directions. In this case, they're opposite. And then when it says complete Newton's second law for each mass below, and I already started, m1 times a is going to be m1g, because it's the heavier object, minus tension. For the second one, it's going to be tension minus m2g. If you remember from 8th grade math, we can do elimination, and the easiest way to eliminate in this case would be to add these two equations. So that's what I'm doing. And notice how now I have m1a plus m2a, which I can then just consolidate into a times the sum of masses. On the right, tension cancels, so I end up with m1g minus m2g. So I can consolidate it as g m1 minus m2. So from there, acceleration is going to be g multiplied by, and then I have my difference of masses, heavy minus light, over the sum of masses. Now I caution you, do not memorize this formula, please. Go through the motions, understand how you put together each equation, how you add them, because case to case, which mass is which changes, and also we will go down to a different configuration where this will be totally different. So do not ever memorize any formulas, please. Learn the process of how you derive those formulas. So now I'm going to take 9.8 and I will multiply that by 108, which is 120 minus 12, over 132, which is 120 plus 12. So 108 divided by 132 is 0.82, and I will multiply that by 9.8, and that gets me 802 meters per second squared. It's a little rounded, so when I'm finding my force of tension and use different equations, I might get slightly different answers, but by 1 Newton or something like that. So let's practice that. It says, solve for tension in the string. So I'm going to take the first equation. That is for the heavy object. So 120 times my 802, which is the found acceleration, will be equal 120. I'm just following the formula, minus tension. So simple trick, if I'm solving an equation, I'm going to take tension to the left with a plus and this with a minus. When you cross the sign, when you cross this line, which is the equation line, cross the line, change the sign. So that will give me tension equals 120 times, so 802 went with a minus, so I'm going to subtract that from 9.8. 802. So that's like 120 times 214 newtons. A lighter object, which is this equation, I'm going to get 12 times 802 equals tension minus 12 times 9.8. Keep tension where it is, grab this with a plus. So tension will be 12, 802 plus 9.8, like 12 times 17.82. All right. So that's how you solve it for the first case. Second case you were doing on your own. Now the difference is that your first object is going to accelerate upward. So like I said, that's your difference. Do not memorize your two equations because now M2 and M1 are switched. So whereas force of tension remains the same, but for your second one, gravity is greater. M1 times acceleration, which is the one on the left, is going to be tension minus M1g. For the second one, M2a equals M2g minus tension. Add the two equations, get a M1 plus M2 equals g times M2 minus M1. 6.5 meters per second. Technically it's 6.53, and because I chopped that tail off, my forces of tension are going to be just a little bit different. Gets me 114 newtons. Look at that, 115, 116 technically, so about 116. So we're a little bit over. In this scenario, I'm giving you the mass that is accelerating downward. I know that my object, whose mass is 48 kilograms, is going to have a greater gravity than tension. Then by default, I know that my other one is going to be with the same tension as this, but smaller mg. Again, I'm going to write out my Newton's second law. M1 times A equals M1g minus tension. And then the second one, M2A, is going to be tension minus mg. The easier way for us to go about this would be to find tension first. Tension from the first equation, I'm rearranging, M1g minus A. 16 newtons. And then I'm going to put in the second equation. M times 588 equals 188.16 minus M1 times 9.8. Grab this over here with a plus, and that will be M1 is 188 16, from where mass equals 188.16. So in case 5, I know the mass of the accelerating up object that accelerates upward, so that tells me that tension for it is going to be less than mg, from where my second object with the same tension will have a greater mg. M1, M2. M1 times acceleration will be tension minus mg, and I can go ahead. It's going to be M1a plus g, which will be 36 times 12.8. I'm just adding 9.8 plus 3. 36 times 12.8 gets me 460.8 newtons. And then I go for M2 acceleration. That is going to be M2g minus tension, from where M2 I can replace tension with 460, and then I know that A is lighter and this can go to the left, and I rearrange that real quick. So mg minus A will be equal to tension, and M2 then will be 460.8 divided by 9.8 minus 3, 460.8 divided by 6.8, 67.8. So about 68 kilograms. So that was for the Atwood machine where both of our objects were hanging. This one, notice that this is a frictionless surface. Then for my object that is on the table, the only force that will matter is force of tension. Because yes, it has gravity, it has normal, and they equal each other. And then it has tension and no friction. Whereas the hanging mass is going to have the same force of tension, only upward now. So this is tension and this is tension, and it has mg, which is greater than tension. Will the system move when released? Yes. This we will calculate a little later. Will it accelerate? Again, yes, because force of gravity. So M2g is greater than tension, so acceleration is not zero definitely. So this one will accelerate this way, that one will accelerate that way. Magnitude is the same for both again. Newton's law. So M1 is the one that is just hanging, so all it has that is unbalanced is tension. M2 is going to be M2g minus tension. Just as before, add them. M1a plus M2a equals M2g, and then you can consolidate that, M2g. So then your acceleration is M2 over M1 plus M2 times g. So the hanging mass is 15, and this is 30, and this is 9.8. So that's 4.9 meters per second squared. The two of them will accelerate with that. Now we can solve for tension in the string. The first equation would be easier. So 15 times 4.9 equals tension, 73.5 newtons. Case 6, additional practice. You can do it on your own. And the actual lab. This was our cart that gave us acceleration from the graph, and this was the weight, and each group had their own. And then from there, they solved it. Now, the thing is, when they calculated the mass of the car ended up being greater than the actual mass. Now, why is that? When you think about this, M1, which was the cart, times acceleration equaled tension, and then the hanging mass, I'm going to use H, times acceleration, was M hanging g minus tension. This was the known number, and this was the unknown number. So if I take my tension from here, I could rearrange this as tension equals the hanging mass times g minus the found acceleration. Well, I'm using one of the data that I got from a group. So they had a 100-gram weight, but when they put that on the scale, it gave them this mass, 116 grams. So you have to convert that to kilograms. And the acceleration that the cart showed was 2.492, 0.10016 times 9.8 minus 2.492. That gets me 0.73, about 20 newtons. I round it after that. Then I'm going to take my mass of the car will be 2937 kilograms. So the calculated mass is 0.2937 kilograms. However, the real mass, when we put the car onto the scale, it read as 0.28183 kilograms. So here's the thing. Why did your car appear to be more than what it is? Think about acceleration is net force over mass. Now your net force in this case was less than what we thought it was because of friction. So reasons for the difference in calculated and actual mass of the car is not zero. It is negligible, but it's not zero. That's why we have a difference. Now for honors only, the actual mass is 0.28183 times acceleration that we measured. So this is mass of the car, this is acceleration, will be equal to tension. What changes now is that car has force of friction in here. So now when I add these two equations, I'm going to have my acceleration times the sum of the masses, car plus the hanging weight, will be equal to tensions still cancel, but now I have mass hanging times G minus force of friction. Mass hanging, 0.10016 times 9.8 minus acceleration is 2.492 times 0.28183 plus, and the hanging mass 0.10016. All that together gets me force of friction 0.29649, so about 0.296 newtons. Or if I use just two sig figs, I can do 0.30 newtons. Force of friction. So this difference in force of friction ended up giving us a different mass.